Okay, good evening. It's February 24, 2023. The time is 10:55. Okay, I will check my camera. Yeah, it's fine. Okay, for tonight, my topic will be Advanced Math, lesson number 13. It's lesson number 13. We are on the application of advanced mathematics, so this is application. And for tonight, the circuit will be, it's an alternating current circuit now, an AC circuit. So a series, resistance and inductance, AC circuit. So meaning to say we are given a resistance and an inductor or inductance connected in series, energized by an alternating current source, AC circuit. The graph of the voltage will be sinusoidal. The upper graph is the voltage. Okay? For AC circuit, if the voltage is AC, the resulting current will also be alternating. And the lower graph is actually the alternating current. So they are both alternating. The voltage is alternating, the current should be alternating. Okay, the problem is asking what will be current as a function of time. Okay, upon closing the switch, what will be current as a function of time? The parameters for the circuit are actually the resistance, the inductance, the value of the E sub m. E sub m is the maximum applied voltage, maximum AC voltage, E sub m. Sine of the quantity omega t plus angle p. Omega is the natural frequency of oscillation. Omega is actually in terms of 2 pi f. It involves AC circuit now, so there is a frequency. So this omega here is actually in terms of 2 pi times the frequency. There's a frequency if it is an AC circuit. Okay. Let's try to compute for I as a function of time with the given condition. The connection is series, energized by an alternating current or an AC source. Okay, the one coming from the utility line. Okay, let's try to bring out the solution. I will check my camera again. Oh, it's still fine. The start of the solution will be upon closing the switch, take the summation of the voltages. The voltage source should be equal to the sum of the voltage across the resistance plus the voltage across the inductance. So a plus E sub m, this is minus, this is plus, okay? Oh, it's alternating, no problem. Okay? This is a plus, so this is a plus. Minus the drop here, okay? Minus the drop across the resistance. Minus the drop across the inductance. We passed by the previous discussions. The voltage across the inductance is actually L times the rate of change of current with respect to time. Okay, and they should be equal to 0. If we try to simplify the summation of voltages, what will come out will be di dt plus the ratio R over L times I equal to E sub m sine of the quantity omega t plus angle p. Okay, this is now the resulting differential equation and how to compute for I as a function of time. It is a part of the solution, okay? So actually what comes out is, I place it here, FONHDE, meaning first order non-homogeneous differential equation. Okay? First order non-homogeneous differential equation is this one. This one. Okay, so to bring out the solution, we must have to, there are two solutions, okay? It will be the complementary plus the particular. Why? Why there are two solutions? Because the right hand side is not equal to 0. It's non-homogeneous. We passed by this equation already. If the right hand side of the resulting equation is not equal to 0, it is non-homogeneous, and the solution should be, there should be a complementary solution and a particular solution. For the complementary solution, as always, this is k a raised to mt. First derivative will be km a raised to mt. So we will take the value of IC and the first derivative, we put back on the resulting, on the derived first order non-homogeneous differential equation. What comes out will be a km a raised to mt plus the ratio r over l times k a raised to mt, and this should be equal to 0. And to simplify this one, we multiply all the terms by k a raised to mt. Okay? There is a common factor, so we must have to eliminate that one. First term multiplied by this k here will disappear. A raised to the mt will disappear. What remains on the first one will just be simply m. Okay? For the second part, if we try to multiply this one by this k here will disappear. A raised to the mt will disappear. Okay? What remains will just be simply r over l. For the right hand side, it's 0 times 1 over this will still be 0. So, upon the multiplication and simplification, what comes out is actually the characteristic equation. Okay? Luckily, it's a linear equation, it's not quadratic. So m now will be negative r over l. Oh, it's just, we are given this equation, m should be equal to, we place this on the left, negative r over l. And that's the value of m. So m is actually negative r over l. So the complementary solution, if we go back here, it will be, we place the constant of the coefficient now to be with the subscript 1. I complementary now, the complementary solution should be k1 e raised to m, which is minus r over l times time. That's the complementary solution. This is a part of the particular solution. It's just a part. Okay? Actually, we are not even halfway, maybe 1/3 way. Okay, let's try to bring out the particular solution. For the particular solution, if we try to inspect the right hand side, e sub m is constant, so actually the right hand side is a sine function. Okay? From our previous examples, if the given right hand side is a sine function, we will assume a particular solution that involves a sine function and cosine function. Because every time we derive, or what we call this, differentiate a sine, there comes a cosine. So we will place a particular solution to be a combination of a cosine function and a sine function. Okay? So I particular should be a first constant A for another unknown constant A times the cosine of omega t plus b plus another constant B sine of omega t plus b. Okay? How did we arrive at this one? From our previous discussions, if the right hand side is a sine function, we will place a particular solution that involves a cosine and a sine with unknown constants. So our only problem is to bring out the particular solution is to compute for the value of A and B. So if this is our assumed particular solution, if we try to take the first derivative, IP prime now, or meaning the first derivative will be, okay, this is easy, guys. A is constant times the cosine function, so it should be that constant times the derivative of the cosine. The derivative of a cosine is negative sine, so this will now be negative times A. Okay? It will become negative sign of the quantity omega t plus angle p times the derivative of the angle inside. The derivative of the angle inside for omega t, it will be just be simply omega times 1. So this is with times omega. Angle p, is constant. So constant. So if we try to take the derivative, it should be 0. So the only coefficient now will be the derivative of this, which is w. So it will now become IP prime now will be negative AW sine of the quantity omega t plus angle p. For the second part, b is constant. This is the sine function, so it will be v times the derivative of the sine function. And the derivative of the sine is plus cosine, so this is still plus. This is b. But the derivative of the angle inside, it will be omega times 1, or just simply omega plus 0. So there is a multiplier here, omega, times the derivative of this originally, which is cosine of the quantity omega t plus 0. Okay? So the first one, it will become negative because this is cosine. The second one, it's still a plus because the derivative of sine is plus cosine, so this plus. So if we try to take the value of IP and IP prime, or IP prime, meaning the first derivative, we put it in the first order non-homogeneous differential equation. We place it back here. What will come out? We will take this value here. The first one is actually the value of IP prime. Okay. The next one is R over L. So there is an R over L here, times the value of the particular solution. The particular solution is actually the quantity A cosine of omega t plus P plus B sine of omega t plus B. The assumed particular solution. And this should be equal to the right hand side. The right hand side is E sub m sine of omega t plus angle B. Okay? It's not complicated. It's just that the angle inside the radicals are what you call this a double angle. Okay, so equating coefficient of like terms, because to compute for the particular solution, we must know the value of A and B. So we will try to formulate an equation that involves the value of A and B. Equating coefficient of like terms now. For all the terms that contain sine of the quantity omega t plus 0, the first one will be negative A omega plus the ratio B times R over L, and this should be equal to E sub m over L. The coefficient of the first sine omega is actually this one. So this is negative, right? Where's the next sine? This one. But we should multiply R by B times L. So this is actual B times the quantity R over L. For the right hand side, okay, sine of omega t plus angle P, the coefficient is the ratio A sub m over L. We call this equation number 1. For the cosine of omega t plus angle P, the cosine is this one. The coefficient is BW. This is BW. Whereas the next cosine, it is this. So it will be R over L times A. Okay, R over L times A. For the right hand side, there is no cosine, right? So we will equate this to 0. Then if we try to compute for B in terms of A plus the other parameters, what will come out will be, small letter b, will be negative R over omega L times A. We call this equation number 2. Okay, board constraints. Okay. Try to solve equation number 1 and number 2. I didn't show you anymore. That's just a linear equation. So if we try to compute simultaneously equation number 1 and number 2 using our knowledge of algebra, A will be negative XL over C squared times E sub n. And the value B will be R over C squared times E sub n. I introduce X sub L over here. X sub L is actually omega L. What you call this, the ohmic value of the inductor. It should be omega times L. And Z is actually the impedance. The real part is actually R, the imaginary part is WL, which is XL, and the hypotenuse is actually the total impedance of the circuit. So the relations of the XL, R, and Z is here. So you just try to, what do you call this, visualize the right triangle. So we now know the value of A, we now know the value of B, okay? So we'll just go back to the assumed particular solution, substitute the value. What will come out? A is actually this one, negative XL over C squared times E sub M. The first one is cosine, right? Cosine of omega t plus angle P. Plus the value B. B is actually R over C squared, this is, times E sub M. Times the sine of quantity omega t plus 0. Then if we try to manipulate this one, there's a common factor E sub M over C, we bring it out. For the first one, we put inside omega L over C, cosine of omega t plus angle P. Okay, we bring out one C here, because the other one is outside. Okay, what will remain inside will just be simply the ratio R over C, times the sine of omega t plus angle P. But if you try to look at the, what you call this, the triangle involving the resistance, inductance, and the impedance, this ratio here is actually sine of theta. This opposite side divided by the hypotenuse is sine of theta. So we could actually represent this one as sine of theta. And the ratio R over Z. Considering theta, R is adjacent, so cosine of theta will be R over Z. So actually this is cosine of theta. Okay? And if we try to simplify, it will come out, what will come out will be E sub M over Z. This is minus sine of theta cosine of the quantity omega t plus angle P plus cosine of theta, this is sine of omega t plus angle P. But this is expansion here is actually, there is an equivalent. The equivalent in terms of a double angle is actually sine of the quantity omega t plus angle P minus theta. You remember the sine of a double angle? Sine of a difference of double angle. If we try to expand this one, okay, where A will be equal to omega t plus angle P and B is actually equal to theta, if we try to expand this one, the expansion is this one. It is this. So actually this expansion, if we try to compress it, it will just be simply the sine of the quantity omega t plus angle P minus theta times E sub M over Z. Okay? So this is now actually the particular solution. So to compute for the general solution, it will be the complementary plus the particular. This is the complementary, the first one, this is the particular. And to bring out the particular solution, at time t equal to 0, current is 0, total current is 0. We place these two conditions here, or we get these two conditions here, we put it here. We could compute for K1. K1, I didn't show you anymore, it's a board constraint. K1 will be the ratio negative E sub M over Z times the quantity sine of angle P minus theta. No more omega, because if we place time to be 0, this will disappear, right? So for the value of K sub 1, it will just be simply negative E sub M over Z times the quantity sine of angle P minus angle theta. So the total particular solution will be, we will just rearrange. This is omega t. I will write first this one, so it's this, right? Plus the value of the K1, but K1 is negative, so I place K1 on the second part. So this is now negative E sub M over C, sine of quantity angle P minus theta. There is an exponential function here because this is the transient part. This times E raised to minus the ratio R over L times time. So this is now current as a function of time. Okay, this is our answer. So if the two parameters are actually resistance and inductance connected in series, energized by an alternating current source, and that E is actually E sub m sine of the quantity omega t plus single p, this is the equation of the current as a function of time. Okay, that's it, guys. Okay, we derived the formula on how to take the value of the current as a function of time with all the given parameters. Because for any given problem, E sub m is given, Z is given, YZ is given. The resistance is given, the inductance is given, so we could compute for the impedance. Z is actually the impedance. Okay? And the ratio R over L, it's still given, right? So the current as a function of time is this formula here. It's a little bit long, so that's why our subject matter is actually advanced mathematics. So for those who are taking up advanced mathematics in relation to transient circuits, this is it, guys. This is for you. So for those who would like to subscribe to my channel is at youtube.com/@ProfDavidJ.Reyes. If you want to share it, please click share. Good evening, Los Angeles.